Happy Thursday. So I am this close to finishing your last assignment, but I couldn't quite get it done today. I will let you know as soon as it's ready. It is going to be a longitudinal two-level model predicting a binomial outcome. I'm going to give you starter code because we didn't have an example on that, but it's exactly the same principle as a logit in that you are using a logit link to predict a probability between 0 and 1 as a percentage. So it's still two levels, it's just in a different context. It's actually using the stuff that we talked about at the end of last time, so we'll go back over that today. It should be right in your wheelhouse, but should hopefully round out your set of examples of things you know how to do. So that's the plan. I will let you know as soon as that is ready, and I will also let you know once your next formative assessment is ready. Please finish that before class on Tuesday so we can go over it. And that's it. So one more week after this, not too much work left to do. We're in the home stretch. So let's start, if you would please, Lecture 7, the crash course in longitudinal. Slide 16 is where I am here. So all the same stuff that we know already, just in a different context. The idea of time nested in person, where time is level 1 and person is level 2. I have up in front of us an empty model. Empty means random intercept model. What is this for? For what purpose would you estimate this model? Like every time I make you do this in your homework, what questions do I ask you about it? ICC. What's an interclass correlation? Give me two definitions, por favor. So we'll do the first one. Variance explained by level 2, more specifically the level 2 random intercept. So when I say intercept, I mean mean differences. So if it were cluster data, it's the proportion of variance that's due to group mean differences. In longitudinal data, it's the proportion of variance that's due to person mean differences. In other words, the proportion of variance that would be cross-sectional in origin. So that's one. That's probably the easiest one to think about. Now the other one, in terms of correlation, correlation between occasions from the same person in longitudinal context, yes. So if I have an interclass correlation of 0.8, that means my occasions are correlated 0.8 with each other within my own self. In cluster data, that would mean my people are correlated 0.8 that are from the same group. So yeah, you can think of that either way. It helps tell us what's going on in terms of what level of predictors are going to be most useful. If most of the variation is level 2 random intercept, you need level 2 predictors. If more of the variation is level 1 residual, you need within predictors. So we had this to start with, and then we talked about fixed and random effects of time, right? Time is a level 1 predictor, so we can have any possible combination of those present in our data. A fixed effect of time means there's some sort of trend on average over time, positive or negative. A random effect of time means whatever trend is there on average does not hold for everybody. So the top two pictures here on slide 18, these show a lack of a random effect of time because whatever slope is present on average holds for everybody. Parallel lines is the idea. That's what a lack of a random slope for time implies. The fact that we still need a random intercept is indicated by the fact that the lines differ from each other on the y-axis. So they're parallel, but they don't all start at the same spot. The bottom two pictures show growth trajectories that vary across the different lines, across the people. So that means we do need a random effect of time. People need their own rates of change relative to whatever the common rate is. And so we looked at equations then. So in terms of terminology, if you're fitting this model here without time, I would call that empty means random intercept because the model for the means contains only a fixed intercept. The model for the variance contains a random intercept variance at level 2 a residual variance at level 1. If we add a fixed effective time, so if we go from picture A to picture B, I would call that a fixed linear time random intercept model. I'm differentiating the fact that thus far, the only parameter that's random is the intercept. So if I say fixed linear time random intercept, that means that everybody shares the same fixed effect. And so that is indicated right here on the equation for beta 1, where the sole determinant of a person's slope is this common shared fixed effect right here. To move to the bottom two pictures, C or D, we would add a random effective time. So now the model has both a fixed slope that everybody shares and a deviation per person from that slope. So U1 in this equation at level 2 for beta 1 is how far off each person's slope is from the common slope, gamma 1,0. So we have a fixed slope and a random slope. So putting those together, homework question, we would call this a random linear time model. So the idea that you have a random slope implies that you also have a fixed. Because the random slope varies around the fixed slope has to be there. So even if this fixed slope were statistically non-significant, we keep it because that is the anchor point for what the random slope is varying around. So likewise, in the empty model, we don't call this a fixed intercept and random intercept model, even though that's what's in here. The fact that we have a random intercept means we also have to have a fixed intercept to go with it. They work as a pair, where random trumps fixed. So if I say I have a random effect, that means I also have the fixed effect in the model. So both go in the code. So this is the intermediate one where the time effect is only fixed, the intercept is random only, and then random linear is when they both, the fixed slope and the random slope for time are both present here. So this is the type of model that you'll be working with in your homework, as well as one level 2 predictor for each of those. So that's one of the first types of models that we looked at. Okay, questions so far? So this model, this right here, time TI, let me talk about that for a second. Time gets a T and an I subscript to convey that each person can have their own set of times. It could be time 0, time 1, time 1.5, times 2 3/4, whatever. So if each person is on a different measurement schedule, either on purpose or because the study somehow got screwed up because real people are real people, what do we call that? Unbalanced, yeah. So one of the hallmarks of multi-level modeling is this capacity to address unbalanced time by treating it as a continuous variable. So time doesn't have to be 1, 2, 3, 4. It can be whatever it happens to be. The other thing that's important to note about just putting time in level 1 means that I am assuming in this model that time varies only within persons. In other words, everybody starts the study at the same point in time. This model would be insufficient if people started the study at different ages or in different grades or at different points along some continuum that you're measuring change across. So this model would be appropriate if everybody starts at the same time. Therefore, time is purely within persons. Another way of saying that is that the intraclass correlation for time as a level 1 predictor would be what? ... Say that again. Time, if it's a purely level 1 predictor, would have an intraclass correlation of what? It's got to be 0 or 1. Which is it? 0. Very good. In contrast, if time were purely level 2, its ICC would be 1. Good. Yes.
So everyone starts at the same time, but like afterwards it's different.
Mm-hmm.
We have different time points. Then I calculate the ICC for time. Would it be close to 0?
It'd be close to 0.
Okay.
If everybody starts at the same time, but they have differences after that because of sort of a systematic shift versus attrition, I would probably handle those somewhat differently. If it's due to attrition, there's something called, what's it called? Pattern mixture model. It's Hedeker and Gibbons. They basically put in the number of occasions that were completed as a level 2 predictor. And so they can estimate different rates of change for people with different levels of completion. And then you can also marginalize those back together based on how many people you have in each category. I would probably take that approach if you're worried about the effect of attrition. If you're worried about like people being systematically early or late, you might calculate sort of an average time or an average lateness or earliness and include that at level 2 as a predictor. We talked about this a little bit after class, but yeah, how you handle person differences in time is somewhat context specific. It's just something to keep your eye out. Anytime the ICC is not 0, you got to worry about this. It's easiest to handle if you're in an accelerated longitudinal design where you know that people either start at different ages or they start at different grades or something like that. Then what I would do is just put in the age where they were when they started as a level 2 predictor, or the grade they were when they started as a level 2 predictor, and that's sort of like a cohort effect. The same thing would be true if you're running a longitudinal study that takes multiple years across multiple cohorts. Like you're repeating the study, say 5 times, because you can only get enough subjects in one go that you need more. Then you would want to control for cohort as a level 2 predictor in the same way. So yeah, this model is simplistic in that this is if time is purely level 1, purely within persons, we don't have to worry about smushing because then it can only have a level 1 effect. The other thing that's noteworthy about this model is simplistic in the type of change it predicts. What does linear mean, folks? Not a trick question. You can make gestures if you want. Yeah. A line? A straight line. Constant change, right? Like if you keep going, you're just going to keep going and going and going and going and going and going. Well, that's not realistic for a lot of outcomes. It's not possible for outcomes that have a ceiling, right? You can't get over 100%, except in my class. Right, because I dish out extra credit for like doing course evaluations and things. Although I don't give you 10% extra credit like some people. I heard about that. I'm like, what the hell? And I meant to bring you oranges, but the first class ate them, so I'm sorry. It's what happens when you have class over lunchtime. But anywho, yeah, so like if you can't go lower than 100 and you can't go higher or lower than 0 and higher than 100 or things like that, right? That's going to have consequences for your pattern of change. So this is simplistic from the point of view that time change is linear. So that's what I wanted to show you briefly are just some alternatives. I have these in the context of time, but really these apply to any continuous predictor. There's no reason why we have to have a linear effect of self-esteem or age or IQ or GPA or GRE score or anything, right? It's possible that any continuous predictor has some kind of nonlinear effect in any kind of regression type model. So these are some options that you might want to consider. So I'm going to cheat ahead here a little bit. Slide 24 is where we're picking up. So what kind of change do you have? We talked about this just a minute ago. What kind of metric of time do you have? And then second, what kind of theoretical process is responsible for change? Oftentimes that can help guide you to a certain type of model, whether it's theoretical or study generated. I want to show you sort of overview just briefly 3 different types of change models. One you're already familiar with, which is polynomial change. So this is where you enter time as a predictor to various powers. So if you just have time by itself, that implies linear change. If you enter time squared, that implies quadratic change, or that you have a change in the linear rate of change. In physics terms, that's referred to as acceleration or deceleration, whereas linear is velocity. If you enter time to the 3rd power in addition, then you have cubic change, which implies that there is a change in how the rate of change changes. I'm not making this up, that's how it is. I read somewhere that this was known as a jerk. I had never seen that before, but I thought it was sort of funny. Like, what kind of jerk puts a cubic trend in their model? That's what I thought. But in these cases, these terms work together to describe an overall curvilinear trajectory that is continuous. So it doesn't have any breakpoints, it doesn't shift abruptly, it's sort of a smooth trajectory, and all of these terms work together. If you have balanced occasions, the number of slopes that you can put in your model to describe the effective time for a fixed effective time is equal to the number of occasions minus 1. That means if I have 3 occasions, I can put in an intercept, a linear trend, and a quadratic trend, and that's it. I have 3 means perfectly captured by my 3 fixed effects. If I have 4 occasions, I can pick up a cubic, and that will completely saturate my 4 means. If I have 5, I can pick up a quintic, I think. Quartic is next. Then quintic, sextic, septic. I think that's the stopping point, right? When you start talking about things going septic, that's pretty bad. In practice, I have seen exactly 1 time where a cubic trend actually made any kind of sense. Past that, I usually say go with something else because the terms are rarely useful. So we had an instance of this, but how you interpret a quadratic effect, the quadratic coefficient is twice how the rate of change changes per unit time. That's the rule. And I have a couple reasons for why this rule is there that you can peruse at your leisure. I just wanted to show you some pictures. So do you remember the 4 kinds of interaction terms, right? Two-way interactions take their constituent main effects and they make them either more positive, more negative, less negative. Same is true for quadratic terms because a quadratic term is just a 2-way interaction of time by time. So what happens is that the linear effect of time, just like any main effect in an interaction, becomes conditional on the interacting variable being 0. Well, the interacting variable is time. So that means the linear slope is specific to when time equals 0. So in each of these pictures, time 0 is at the beginning, so I've centered so that time 0 is the first observation in the study. In the first picture here on the top left, the linear slope is a positive 4. So I've tried to draw little lines here to indicate the slope of the curve at that point. If you remember from calculus or physics, that you'd say that's the slope of the line that's tangent to the curve at that point, or the instantaneous linear rate of change. What happens to this positive slope of 4 given a positive quadratic slope of 0.3? That linear slope becomes more positive by twice the quadratic, or 0.6 per unit time. So 1 unit later, my slope of 4 becomes a slope of 4.6, then 5.2, then 5.8, and so on. So if it's positive and positive, I would call that an accelerating positive function, where growth speeds up. This might happen, say, if you leave a sponge filled with dirty dishes in your sink and you're measuring the growth of bacteria. Right? Just multiplies. You know, or you visit a preschool and a bunch of kids hug you. Then all the germs on you just multiply. In contrast, if I start off with a positive linear slope, but now I pair it with a negative quadratic, it works against it. In this case, the linear slope becomes less positive by twice the quadratic of 0.6. So it starts out at 4, it slows down to 3.4, slows down to 2.8, and so on. So the rate of change is slowing down. The same thing in opposite direction happens in the bottom left square. I have a linear rate of change that's negative that slows down due to a positive quadratic. And then another case of acceleration in the last square on the bottom here on the right. A negative slope paired with a negative quadratic means accelerating negative decline. So these are pretty common. Quadratic slopes are often used to describe maybe 4 or 5 occasions that are a little bit bendy. The reason is that it's easy to do because it's still a linear model. It's linear in the sense that it's still slope times variable plus slope times variable plus slope times variable. That linear formation still works to capture this nonlinear trend because the terms that are being multiplied by the slopes are squared terms or cubed terms or so forth. So this is perfectly fine from a sort of data pragmatic perspective. It's sort of crappy from a theoretical perspective. Because what, for this top right here, what does this curve predict is going to happen if I were to keep measuring people? Yeah, I'll take gestures. Come back down. So like if you're measuring growth in school or achievement, you're saying that the longer they go, they're eventually going to get dumb again? That doesn't seem very plausible. Or if you're measuring, say, decline from aging, they're eventually going to get better again if you just keep measuring. Not very plausible. So quadratics are somewhat theoretically dissatisfying, but they're pretty common. Just remember that it's twice the quadratic is how the linear rate of change changes. You can have fixed and random quadratics, and the same thing would apply. So a fixed effect describes what happens on average. A random effect describes how you vary from it. So in this slide here, 31, I have an example of what I would call a random quadratic time model. So at level 1, I have 3 betas, an individual intercept, individual linear slope, an individual quadratic slope. Because I have 3 betas at level 1, I need 3 level 2 equations. Each one, the first term refers to which beta we're talking about. The second of the subscripts refers to the order in the level 2 equation. So the red terms here are the fixed effects. So gamma 00 is the average intercept, gamma 10 is the average linear slope, gamma 20 is the average quadratic slope. The u's then are how far off from the average you are. Your intercept, your linear slope, your quadratic slope. And the rule in terms of random effects is number of occasions minus 2. So to fit this model, I need 4 occasions per person at a minimum for it to be identified. All of the random effects become conditional in the same way as the fixed effects. We don't need to belabor that. So this is one approach for nonlinear terms. Here's another. And this is one that I wish more people knew about because I find it exceedingly useful. I refer to these as piecewise models. They're also known as linear splines. They show up in things like regression discontinuity designs and regression splines and stuff like that. Have you heard those words? It means basically you have 2 slopes joined together at a knot, and different types of models, either you know where the knot is a priori and you set your predictor variables up that way on purpose, or you ask the model to find the knot. The latter, where the model has to estimate the knot as another parameter, those are known as latent knot, or trying to think of the other words for it. Yeah, latent knot or unknown knot, something like that. The ones that I'm showing you here are the former, where you know where the knot is. So here is an example from a former student. This was a multiple baseline intervention study designed to increase positive behaviors in 5th graders. And so they had a period of measurement during baseline where they did nothing, and so they're pretty much flat. They did their treatment, and lo and behold, behavior jumps up, and it gets better and better and better. And then they take their reinforcement away, and they start sucking again immediately, and they just keep sucking. And then they bring it back, and they get better and better and better and better. So if I were to think of this as sort of a continuous trajectory, right, if I didn't know about these differences in what happened, that would be like, what, a 5th order polynomial, like weaving my way through there? But that wouldn't allow me to test the basic hypothesis of whether this intervention approach works. To do that, what I want to know is if there's a significant shift in the intercept from baseline to treatment, back down from treatment to baseline and back up, as well as potentially changes in the slopes for each of these periods. And so a piecewise model would allow us to directly fit an intercept and a slope through these periods and test the differences between them. So anytime you have a study design where something different happened at some point, and you know about it, any kind of before and after, these sorts of models are very useful. The only catch, as I said, is that you have to know where the breakpoint is. So for instance, I once had a developmental psychology student ask me, can I use this for before and after puberty? Do you know what I said? I said, sure. Just make sure you have a date in the data set when puberty happened, right? Like Tuesday, now Wednesday, you're fixed, right? And you're good. Now there are measures of pubertiness or whatever that they have, but that's still kind of an approximation. So if you don't really know when the cut point is for something like that, you'd be better off with one of those latent knot models where you're trying to estimate it. And believe it or not, if you have enough data, you can actually make the breakpoint a random effect where each person could have their own as well. And that would work well for something like puberty, which is sort of age normative, but there's a lot of variation in how kids change. Here's an example of how these models have commonly been used in practice. This is cortisol data. So I know a tiny bit about cortisol from working with other people who care about it. What I do know is that immediately after you wake up, your cortisol spikes, and then about 30 minutes later, and then the rest of the day, it sort of falls down. And how quickly it falls down and whether or not you have a flat slope or a steep slope is supposed to be an indicator of health. Flat slopes are bad, I think. And so this phase right here is known as a morning rise, and this second phase here is known as an afternoon decline. But you'll note that my orange line here doesn't look like it fits very well, huh? Can you think of anything I could do to make this orange line fit a little better? Quadratic it. Yeah. So even though these are piecewise linear models by name, they don't have to be linear. Each piece could be quadratic or exponential or what have you as needed. And with 4 occasions, I would have enough to do that. So this is what the SAS code would look like to code something like this, given that each person has a different set of occasions. This is an example of unbalanced time because the instructions given to these participants were take a saliva sample, they chew on a cotton ball, that's how they measure cortisol. When you wake up, 30 minutes later, whenever you have lunch, and whenever you go to bed. Right? Even the same person across a week would probably have a lot of variability in when those times are. So I can't just call this time 1, time 2. I would be losing a lot of important information, especially with respect to trying to fit these trajectories. So this set of code requires you to have 4 variables in columns as to when time 1 was, when time 2 was, when time 3 was, and when time 4 was. And then you could use this code to subtract. So it's the difference in time from 1 to 2 that makes up this. The second slope is off. If occasion equals 3, then the first slope stays right where it is, and the second slope picks up. So this coding scheme makes it so that the purple variable, P1, directly indicates this part of the curve, the morning rise, and then after time 2, the orange variable, the P2, kicks in and represents this part. And so then you can see what aspects of someone's life predict differences in P1 versus differences in P2 as separate measures. So that's piecewise models. This type of thing would also be useful anytime you have a predictor that is both sort of categorical and continuous and you're not sure what to do with it. Like if you gave a survey to undergraduates about their history of sexual abuse, let's say, something where you have mixed populations. Now hopefully, right, what kind of distribution would we like to see on such survey? Assuming we're not evil people. Huh? What? Poisson? No, what in an ideal world, what kind of distribution would we like to see? No. No, evil, bad. 0, degenerate, right? Like everybody has no abuse, right? Like that would be the best possible outcome. No, abnormal. But no, you're going to have a bunch of people, no matter how many questions you ask, right? If you want to increase reliability of measuring a construct, right? You're supposed to get more questions and more better questions. Well, if you're somebody who fortunately has never been in an abusive situation, If you give me 10 questions, you give me 100, it's no, 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 no. So there's always going to be a pile of people that are like, no. And then unfortunately, there's a pile of people who are like, yes, and then there's a question of how severe it was. Well, if you think of that as a continuous variable, there's a big difference between going from no to a little bit, like just that hump, even if it's going from 0 to 1 numerically, like that is a big deal. And then from going to 1 to 2 to 3 to 4 to 5, like that's a different population, a different construct. So something like this could be used to say, did you ever have any kind of abuse happen to you? Yes or no? That's one piece. And that differentiates people who are not abused from abused at all. And then among the abused people, so sort of like picking up from here, you could have a slope that looks like that captures the effect of additional severity within that subpopulation. So you can think of that as a nested effect or as a piecewise model. Same thing with something like number of chronic illnesses you have. That's a common variable. Nothing's wrong with me versus one thing is wrong with me. Well, if that one thing is cancer, that's a big deal. So going from 0 to 1, 1 to 2, there's different ways that you can think of continuous variables in sort of chunks like this. And these piecewise models, I think, are very useful in capturing those kinds of phenomena. So I did an example in chapter 6 of my book where I cheated a piecewise model just to capture a nonlinear trajectory that looked like this. So there's empirical ways to use these besides just theoretical. I'm going to skip some of this stuff. Here's another one. This is slide 41. This shows the fit of a quadratic model, which is red, to response times across 30 trials. A latent two-piece model, that's the green line where the computer algorithm decided where the knot was. And then this other one, which is blue, which is a negative exponential. So the negative exponential, the blue line, that is what's known as a truly nonlinear model because it has an exponent in it. Those are way harder to fit, but they're good in the sense that they have, as one of their parameters, an asymptote. So rather than the quadratic, like saying you're going to come back up, the exponential says, no, once you're done changing, you're done. And you can measure individual differences in where you end up, as well as individual differences in where you start, or how fast you change, or the total amount of your change. And so those are what's known as truly nonlinear models. They're difficult to fit, and I figured out that you can cheat it by simply taking a log transformation of your predictor. So this is going in the next edition of my book, which I'm supposedly working on right now. Sorry, publishers. If you log transform time and you fit a linear effect of log time, you get this black line right here. Looks kind of exponentially, right? If you add a quadratic effect of log time, the red line here is what happens if you have a positive quadratic, and the blue line is what happens if you have a negative. Now that looks a whole lot like a negative exponential. So in practice, I think putting a logged version of a predictor in to mimic an exponential curve is probably a really useful technique because then you don't have to fit a truly nonlinear model, which makes it easier to estimate and you have a lot more software advantages. And so on the bottom pictures, I'm showing the natural log version of time instead, and that's where you can see that a linear effect of log time is indeed a straight line with respect to log time. It shows up as an exponential curve with respect to original time. So those are your other things to do with time. So in a nutshell, wake up, guys. In a nutshell, question?
Yeah, but how do we explain the log time?
How do you explain it?
Yeah.
You don't. You just put up these pictures.
Okay.
It's the change in y for a unit change in log time, whatever the hell that is.
Okay.
Because yeah, it's equal units in log time do not translate into equal units in original time. But that's actually the advantage. It's a way to create an exponential curve without having to fit a nonlinear model. But yeah. So your crash course in longitudinal. Why is longitudinal a lot more challenging than just multi-level? Time. Not only do you have to have fixed and random effects of time, but they have to have the right shape. All of that has to happen before you can talk about effects of any other level 1 or level 2 predictors. And after you control for fixed and random effects of time, you have to determine whether or not your residuals are still more related than the model predicts, in which case you want to try out different kinds of residual covariance. So there's a whole lot of fitting that goes on with respect to time before you even get to the stuff you care about. So that's why in this class, we went straight from empty model to level 2 predictors in the same lecture. In my longitudinal class, that same progression took 8 weeks. You remember? Now you know why, right? Remember all this stuff? It's all complicated and stuff. So that's why I'm trying to be nice in your last homework. I gave you linear time. Right, Molly? She's like, that's nice. Are you sure? No, it is. It's a 2-level model with linear time, and I want you to see whether or not linear change differs between 2 groups. That's it. So little interaction-y, little novice stuff with respect to time. So, okay. But what I really wanted to talk about is 3-level models. Yeah! See, if they'd let me, I could come up with like 4 different classes on this stuff, easily. It's complicated. But let's do 3-level models. So I don't know how far into this we'll get today and next week, and so that's why I didn't make a homework on it. Because there are lots of different kinds of 3-level designs, and it's not always obvious which level is which. Time is not always on the bottom. So I wanted to start there. So one question I get frequently from people is, how do you know how many levels you have? The answer is always, it depends on your outcome. It does not depend on your predictors at all. So if, for instance, I have a longitudinal model and I've sampled 1 person per family, then that is a 2-level model regardless of whether I'm thinking of some of my predictors as family-level characteristics, person-level characteristics, or time-level characteristics. In that type of design, if I have 1 person per family, family and person are the same thing. If I were to sample 2 or more people from a family, so I've got mom and kid or siblings, parents, etc., that would be a 3-level model because time is nested in person is nested in family. And so then family characteristics are level 3, person characteristics would be level 2, time varying characteristics would be level 1. If I did that same study in multiple places, different cities, different countries, etc., that's 4 levels. So it depends on the outcome, not which level of predictors that you have. And in this last case here, what if I did my study across, say, 20 cities, and I don't care about cities, so I'm just going to treat a 3-level model? Am I allowed to not care? Nope. What if I tell you, but I don't have any variables about city, I just needed more data? What do you tell me? Yes and no. But what if I don't have any questions about city? Can I just pretend that I don't have multiple cities? What would be the danger in doing that? If I pretend that families are independent, what do you think about that? Can you think of a way I might quantify whether or not how independent families are? Some kind of intra-class correlation, maybe? Yeah. And yeah, even though I didn't measure any city level variables, do I actually have some? To the extent that families from the same city are similar, then the city mean across families is a variable. It might not be a good one to the extent that the families aren't representative, but it is a variable. So yeah, it doesn't matter whether you have predictors at each level. If you have an outcome that is measured such that there is dependency across your sampling, that's when you know you need the levels. So that means that when we talk about a level, we're talking about, at a minimum, one variance component per sampling dimension, a random intercept at a minimum, potentially random slopes of lower level predictors as well. So here's one kind of design that would take 3 levels. This is what's known as a clustered longitudinal design. So for instance, if I had the same people participate more than one time in a survey, so it's longitudinal measures of people, and people are nested in countries. They do not move. Then time is level 1. Respondents, people, are level 2. Countries are level 3. That's fairly straightforward. The effects of time-varying predictors, then, those can be included at level 2 in that the average of the time-varying predictor becomes a person thing. The average of those person things become a country thing. You can have countries. You can have time-varying effects of country-level things at level 1 and level 3. So in this type of design, you might have country characteristics that are measured across time. They would go in level 1 and their mean at level 3. If I have person-level characteristics that are measured across time, they would go in level 1 and level 2, and their means across people would go at level 3. So time-varying predictors get to be extra tricky in these sorts of designs. Another one that is more popular in political science and sociology and those kinds of places. Anybody from there left in here? Nope. I had a few sociologists at the beginning of the semester, but they left. I hope they'll come back someday. This type of design. Let's see here. No, not this one. This is one that I had. The next one is from sociology. Yeah, this is one that was from Survey Research Methods at Nebraska. I had a student that had this kind of design. I had never seen it before. So this is where we have different respondents in every year. It's the same survey, though. And so respondents are nested in interviewers, but it's a different set of interviewers and respondents each year. So year, time, is actually level 3. Within a year, you have a set of interviewers. Within each interviewer, you have a set of respondents. And you do this for multiple years in a row. So is this a longitudinal study? Yep, different respondents each year, different interviewers each year. It's just this process is repeated.
So you can look at them individually?
You could look at individual responses, but they're not, people aren't changing. I mean, you can't say that. I have a hard time with this one. My instinct is to say it's not longitudinal because you just have like cross sections of things. Because you really have to believe that this procedure that you're going through for your sampling is comparable enough to be like, yeah, concern for the environment is going up over time, right? It's not that you're grabbing different kinds of people or something like that as time goes on. So in this case, how you treat years would depend on how many there are and whether or not you have predictors in that level. If you don't have that many years and or you don't care about year, you could put it in as a fixed effect. This is 1990 versus 91 versus 92. Done. Don't care. If you do care about why responses are different in 1990 than in 91, you would put in things that were different in 1990 versus 91. I don't know what those are, but presumably you would. So yeah, time is actually level 3 in this type of design. The sociology/political science one is this one, where they view this as a longitudinal study of countries. So a country is measured repeatedly over time, and it's the same country. But each time they go out, they grab different people. That face. I'm like, ugh, that makes me very squishy. You really have to be willing to believe that the people that show up in year 1 are functionally the same as the people who show up in year 2 to be able to talk about how the country changes. So then you get into things like sampling weights and representation and all that kind of stuff. But in this case, time is level 2. Because respondents are nested in years. So whether or not you could actually treat this design as 3-level depends on what level your outcome is. So if you have time-varying country outcomes, respondents are irrelevant. They're gone. The only way that you could incorporate respondent-level information as a predictor would be to aggregate responses across respondents for that year. Because if you don't have a respondent-level outcome, they are not part of the model. If it's a year-specific outcome, you have to aggregate the lower-level information up. Otherwise, there's nothing for the model to predict. So yeah, lots of different kinds of 3-level designs. Do any of you have the pleasure of having a 3-level design in your life? Really? Nobody? I find that improbable. Maybe you're like, I do, but I'm not talking. I don't want to talk about it. Okay. Well, I will. The example that I have for you is time within person within twin pair. So it's going to be most like this one, where people are nested in families in the same way that they might be nested in countries. Because even if you don't like your twin, you can't change families. So I have for you an empty 3-level model. And I'm going back to convention because in acknowledging that the levels could be any combination, I'm going Tij for my subscripts. So this is what it would look like if I had time is level 1, which is T, individual is level 2, which is person here, and J is group for level 3, which is spelled wrong. Because group starts with a G. See, J is spelled wrong. Come on. No, nothing? She's like, no, you're not funny. Look, you guys are paying like $17,000 a semester in tuition. I feel like I got to put on a show. I sang for my other class. I did. Don't make me. Don't make me pull that out. I was talking about the analogy is like, I haven't seen a ticket this expensive unless you were like, Britney Spears playing Vegas or something. So, but no, my show is a lot more expensive than hers, so I really gotta kick it up. But I bet she can't do 3-level models. All right, level 1, YTIJ. Beta placeholder plus E. That part's the same. Level 2 is different. Beta placeholder equals another placeholder. This is delta. So beta 0 is the level 2 intercept placeholder. Delta 00J is the level 3 intercept placeholder, which comes down here. So if I start at level 3, each group gets its own intercept as a function of the fixed intercept, which now has 0, 0, 0, plus the group's random intercept, and in my book I gave it a V, which I'm going to have to change next time because I already used V for V matrix, so my bad. I was literally thinking TUV, like in the alphabet, because I used U for level 2. But I didn't want to reuse U with a different subscript because that gets confusing. But it's V for right now. So fixed intercept, that is the average mean of the group means, plus V00J as the random intercept at level 3. How far off your group is from the grand mean of the group means. Okay? So these two together get you to what your group prediction is. Now this falls over here into level 2. Based on your group, where are you? UOIJ is how far off you are from your group's mean. Now we pull that down to level 1. Where are you? Great. Where are you today? E is how far off you are this occasion relative to your mean. So if you wanted to write this same model in a straightforward single line version, the composite equation is right here. So it has one fixed effect, gamma 0, 0, 0, the fixed intercept, the mean of the group means, plus how far off your group is, plus how far off you are from your group, plus how far off today is from your mean. So 3 variance components, 2 different kinds of random intercepts, and a level 1 residual. They're all uncorrelated because that is the definition of what a level means. Variance components are always unrelated across levels. So that's my empty means 3-level random intercept model. Now when I started class today, I asked you, what do we use empty means models for? Like, what do I always ask you in your homework for this type of model? Remember that? It was at 2 o'clock. It wasn't that long ago, I swear. ICC. Oh, can you think about how I might make an ICC out of this giant mess? At least 2. There's lots of different kinds I could do. So I want to show you a variety of ICCs. Because which ones are more or less useful depends on your design. So let's go back to 2-level. Let's say that we're ignoring groups, it's just person and time. So first thing we have, once upon a time there was an E, all the variance in one pile. Then we split the variance into level 2, which is between persons, level 2 random intercept, and within persons, level 1 residual. So we had an intra-class correlation that went along with this, which was of the total, how much is between at level 2 and the intercept, right? That's my 2-level ICC. And because there's only 2 variances, there's only one possible ICC. That's it. If I know the ICC is 0.8, then I know 1 minus the ICC is 0.2, the end. Okay, now, note the color switch. I'm very proud of this. Because they're all smushed together. There's 3 colors, see? Not quite worth $17,000, but I'm trying. Although to be fair, that's a whole semester that's across all your classes. I might only have to do like 3,000 or so. And if we prorate that across classes, maybe it's only like, what, $250 or so? That's a good deal. That's like, you know, Hall & Oates tickets or something. Okay, so what I just said, in a 3-level design, if I start with all the variance in one pile, split it into what is level 1 and level 2. I'm labeling this the ICC for level 2 because it's out of the total, how much is person level 2 intercept variance. Now this one splits. Show that again. Of what I called level 2, because people are nested in groups, I also want to know of that total between person variation, how much of it is actually due to groups. So that level 2 random intercept variance itself splits. And now I have what is between groups at level 3 versus what is within groups at level 2. This part is where we started our semester. This is cluster data. How much of person variation is actually group relative to within group, right? So I can have an intraclass correlation at level 3 that says out of the level 2 and above variance, out of what I'm calling person, how much of that is group? That's my level 3 ICC. My level 3 ICC ignores level 1 because I've already split that off. So in this type of design, if I have time within person, within group, the level 2 ICC tells me how much is between person and above, tells me how much is cross-sectional. How much is not time? Of that cross-sectional not time between person variance, how much is between groups? Here's some equations. This is what I just said with symbols. So the ICC at level 2 is between person over total, where between person is actually 2 and 3. Because if you don't split it, if you just fit a 2-level model, all of that level 3 variation is still embedded in level 2. It's smushed together, essentially. And so what is level 2 and above over total? That gives you the expected percent variance that is due to between person differences or the expected correlation of occasions from the same person. How much of it is cross-sectional in this type of design? Now the new one. This is different. ICC for level 3 relative to level 2 only, ignoring level 1. Level 1 is gone. What I'm trying to do is zero in on this numerator right here, what I called between person, and decompose that. So of what I called between person here on the bottom, how much of that is actually between groups? How much of that is level 3? So it's 3 over 3 plus 2. So this is the expected correlation of persons from the same group. It's also your effect size for whether or not you need to worry about group. Okay. Want to go back to the picture? Okay. All right. How are we doing?
Use that as a kind of a screen if, for example, like level 3 of ICC is pretty low, like that 0.01 or 2. So maybe we just don't even think about the 3 levels at all.
I would say that it's useful to report it as an effect size, even if it is non-significant in, or even 0. I would say that you still have to worry about it to the extent that once you start explaining variance at the lower levels of the model, that intercept variance at the top level will be higher because they're yoked together. The only situation in which you don't have to worry about level 3 is if the intraclass correlation is exactly 0, in which case, then there is no design effect, and people are functionally independent, but that will change after you explain variance. So they'll appear that way in the empty model, may not stay that way. The only other situation, when you have one person per group, right? If you have one person per group, then groups are independent, people are independent, because people are groups. Which, by the way, is what happens if you were to include samples in which there is only one person per group. Because you can't differentiate those two, their variability goes up to group.
What if you have some group that has 1 person, some groups with?
That's what I'm talking about. So if you had this kind of design and you had some groups that had only one person and some groups that had 2 to 10 to 15, whatever, the groups that have one person, their variability will go up to the group level because it can't be differentiated. And the groups that have more than one person, basically their group average goes up to level 3, and level 2 are the differences within people from the same group. So that the risk you have in including groups with only one person is potentially biasing your level 3 component because it will look like there's more there because the singletons are groups.
That would better, we just combine them together. Just one.
Because you can't differentiate them, their variability goes to 3. If a person is a group, then it goes to group. Level 2 would only be relevant if there's more than one person per group in which it distinguishes among the people relative to the group average.
Yeah, but I mean, if there's just one person per group, and like you have a bunch of this kind of case, you can just combine them together.
One person per group, and what else did you say?
And you just combine them together.
Combine them together?
Yeah, as a group.
Oh, a group of singletons?
Kind of like that.
That's interesting. Maybe that would be okay. I don't know what I would do with any between group variability in that case. Like, I don't know what I would think of that as a construct. Because then it'd be like, what do they have in common other than that they're singletons? Maybe if being a singleton were relevant, like if you had maybe like single parents or a single child, like then you had a group of single children kind of thing, like then single children are weird and, you know, multiple children aren't kind of thing. Like if you had some way of making sense of what their commonality would be. Otherwise, I mean, you could do it, but I don't know what it would mean. So not wrong, but weird, maybe. Yeah. Okay. So yes, these are 2 intra-class correlations of the possibles. Level 2 is what Stata gives you if you ask for ICC. What Stata gives you for level 3 is not this. What M+ gives you for intra-class correlation at level 3 is also not this. Would you like to know what it is? Because a lot of people mess this up. It is actually, I think it's down the road here. Level 3 intra-class correlation according to Stata and M+, is like this one. It's level 3 over total. That's what they give you. So that would be the proportion of total variation that is between groups, just a straight proportion. It would also be the expected correlation of occasions from the same group, but not necessarily from the same person. Yeah, in that face, I'm like, what does that tell you? So I don't like that one. Another thing that people commonly do, they report proportions of variance and call them ICCs, and that is not correct either, because that is not the expected correlation of anything. So you have to be very careful in describing these things what you mean. If you want to just give the straight proportion, that's fine. Just don't call it an intra-class correlation. Like of the total variability, 20% was over time, 50% was due to persons, and the remaining 30% was due to groups, right? That's fine. And then you can combine those percentages into these various things if you want to, but the proportions are just proportions. Here's an alternative type of design. Jianpeng, this one's for you. And also Jinghong, you guys are they're working on a research study that's intensive longitudinal data, where it's multiple samples per day over multiple days for multiple people. There were a lot of people in my last class who had this type of design, and so I did a whole homework on it. I was tempted to give it to you guys, but then I thought, no, that'd just be too mean. So we have occasions within days within persons. So in this case, I would actually start differently. I would fit a model that differentiates person at level 3 first, and then leave level 2 and 1 together sort of smushed. So how much is person cross-sectional versus within person over time? So that's 3 versus 2 and 1. Then you can separate out 2 and 1 as of what I'm calling over time, how much is between days and within days. Because that's a common question in these sorts of designs, is it 2 level or 3 level? If I have multiple occasions per days over multiple days, do I just have a whole lot of times within a person? Or does it matter if they have multiple occasions per day, do I need to keep track of which day it is? And that's an empirical question. So I would do this instead. which is of the total variation that is all together, how much is at level 3 between persons? I call that in my book ICC level 3B. This is what M plus and Stata give you. It's just the proportion of total that's between persons. In this kind of design, that is useful because that is telling you how much is cross-sectional, period, relative to longitudinal, because longitudinal takes up level 1 and 2. Then you can go into what is level 1 and 2 together and pull those apart. And of level 1 and 2 combined, how much is level 2? I'm calling that ICC level 2B. Because that is your official test as to whether or not there is a higher correlation of occasions from the same day or not. Is it just occasions from the same person and that's all that matters, or do you also need to know from which day the occasion came? ICC level 2B tells you that. So, there you go. But it gets worse. You're like, can it get worse? Let me go back this picture here. So if I can split out an intercept into what is within and between person, guess what else I can also split out? What other kind of random effect can you think of besides intercept? Slope, yeah. I can have random slopes at level 2 and level 3 for both. So in a 2-level model of independent persons, slope variance comes out of residual. So I take what I'm used to thinking of as within person variation. I know that some of it is systematic, the fact that some people change differently. It's still error in the sense that I don't know why, but that becomes a level 2 variance component. In a 3-level model, we have the same idea. So we're starting from here, where I have a level 3 random intercept, a level 2 random intercept, and a level 1 residual. So first step is similar. Out of the level 1 residual, if I want to test a random effect of time across persons, level 1 splits. And I have level 2 person slope variation versus within person variation. Why are you off your line today? In the same way that I split person intercept variation into group versus person, I can take person slope variation and split that into group versus person. So now we have, why are some groups starting out higher than others? Why do some groups change faster than others? Within a group, why do some people start out relatively higher than others? Why do some people change relatively faster than others? And then at level 1, why are you off your line today? Error around the growth trajectory. So variance components at the same level get a covariance. So the intercepts and slopes from the same person get a covariance at level 2. The intercepts and slopes from the same group get a covariance at level 3. And level 1 is uncorrelated with everything. And we can actually do intraclass correlations of these level 2 and level 3 intercepts and slopes in the same way. So if we're talking about person intercepts specifically, relative to the total intercept variation across 2 and 3, I can figure out how much of that is at 3. So that's ICC level 3, just like from before. I can also take of the total time slope variation across levels 2 and 3, how much of that is between groups at level 3. That's an ICC for the slope specifically. How much of the slope variation is shared between groups relative to individuals within a group? So I think that's what, like 10 different ICCs in the last 10 minutes, give or take? So yeah, the moral of the story is if you're going to use the word ICC, give them the formula. Calculate it as, because the word ICC is not sufficiently descriptive in 3-level models at all. But here's what it would look like. So if I added time at level 1, That beta placeholder now has a level 2 equation. That requires a level 3 placeholder, which comes down here. So the level 3 model holds 2 fixed effects, fixed intercept, fixed time slope. Each has a group-specific deviation, how far off the intercept your group is, how far off the slope your group is. Once your group gets its own intercept and slope, they come to level 2. Now it's your turn. How far off are you from your group's intercept? U0. How far off are you from your group's slope? U1. Okay, now I got my own slope. I come back up here to level 1. Now, how far off am I today from where my slope put me? That's E. No? Whoa, I know, right? You look a touch overwhelmed. Would that be fair to say? Or just tired? I will tell you that it took me a good 10 years to get this right. I'm not exaggerating. Especially the equations. That took a long time to get right. And when I first learned this, I did not understand how you could have random intercepts and slopes at 2 and 3 and how they were not redundant somehow. And I was fortunate enough to have Don Hedeker come and give a workshop at KU when I was a grad student. And I asked him that question. And he turned to the board and he started drawing. And 10 minutes later, I totally understood. And so it is with great pleasure next class that I will give you the drawing that he showed me. So passing it forward, thank you, Don Hedeker, for helping me understand 3-level models. So we'll pick up there. But for your next quiz, I'm going to ask you about some interclass correlation stuff. So nothing too challenging, but that's what it's going to be about, just to give you a heads up. I'll let you know when it's ready, as well as your very last homework. Okay? Okay. Now go have a great weekend. Teacher's orders. Yeah, we can. Hang in there. One way or the other, this semester will end soon.